Welcome back, everybody. AP Chemistry. This is Unit 6, Section 4. We're taking a look at the forces between atoms themselves and the forces between molecules, or what we call intermolecular forces, and IMFs. All right, so there is a difference between the forces we've been studying to this point of intramolecular forces and what's coming up in the new material for intermolecular forces. So let's review a little bit of those intramolecular forces that we've been talking about. Throughout this entire year to this point, there are forces that hold atoms together. And so when you see intra, be thinking about atoms. Okay, that's within the molecule itself. And there's three different types out there that are going to be present. All right, so let's take a look, first of all, about the metallic bonds that hold atoms together. Now, metallic bonds are a little bit different, and what holds these metallic atoms together is basically a sea of atoms, or a sea of electrons. So think about a sea of electrons holding these atoms together. And so if we have an atom, a metallic atom, we have the proton in the nucleus, and we have electrons out here, and they're just going to be stacked up like this within that compound. And so if we have another atom down here, like it's a thin sheet, we would have those electrons just kind of sitting on the outside of this. And essentially what's going to happen when we have a metallic compound is it ends up being no electron is assigned to any one particular atom. It's actually free floating and going through the entire thing. And that's what we mean by a sea of electrons that go in there. Now, how these would be ranked is according to their lattice energy. Okay, so think about your periodic trends. And so if we're going to be comparing something like lithium and sodium and then tin and then copper, these would be going weak forces to strong forces because of those periodic trends. Now, a second type that we'd find out there would be ionic compounds. Okay, ionic compounds, we teach this all the time. Think about an electron transferring from one atom to another, and that's what's holding it in place. Okay, so for example, we had our salt that we always typically use with that. Remember, that will dissociate into sodium positive ion and the chloride ion. So chlorine will pick up one of the electrons, and so when we get a compound that's ionic in nature, how it will come together in a compound is basically these positive ions and negative ions are going to stack up one on one another, and this forms more of a crystalline structure. Okay, and so here would be my salt crystal. And you get the idea with that transfer of electrons holding those together. Okay, now what holds, how we would associate the different strengths with those types of compounds would be following Coulomb's law. If we have a greater difference between those charges, if you remember what Coulomb's law is all about, here's a 2 to 2 charge, here's a 2 to 1 charge, and here's a 3 to 1 charge. So Coulomb's law is going to be the one that we'll be following to figure out the strength of those bonds, holding them together. And lastly, we have our covalent bonds. Okay, covalent bonds are for our nonmetals that are sticking together, and then we'd be thinking about an example like water. Okay, so if we're looking at something like water, remember we did the Vesper theory, and we are sharing those electrons. That's the key word with covalent, is the sharing of electrons back and forth. And so we see that going back and forth here, and that holds those atoms very tightly together. And we can take a look at those in terms of other types. Now, this would be a polar covalent. We have non-polar covalent bonds as well, like, for example, diatomic fluorine. Okay, there's a sharing of electrons back and forth here. So if we're going to be ranking these from weakest to strongest, we would definitely see that the weakest would be my metallic, then followed by the ionic, and lastly followed by the covalent. And again, we can sort through our metallic ones based on periodic trends, and we could take a look at my ionic based off of Coulomb's law, and then we take a look at the covalent. If we were to rank those within the covalent realm, we would take a look at the polarities. All right, so that's just a quick review of those things that we would find to be the intramolecular forces. Now we've got the intermolecular forces. Okay, intermolecular forces are a little bit different in that we're going to be seeing these molecules are sticking together, but now we're going to find times that they are going to, even though they're neutral in themselves, they're going to find times, say for example, we have the example of water, And overall, it's neutral, but we see that we've got a polar side over here. Okay, and there are times when it's going to be even like the example of diatomic fluorine, even though it's nonpolar, we've got all these electrons around there, and in fact, they are in constant motion. There are going to be some rare times when we find that they get stacked up on one side, making it very temporarily polar on one side, even though it's going to be, in nature, it's going to be neutral. So those types of forces that will be that I'm describing are going to be ones that we find just accidentally. Electrons are going to be stacked up on one side, and we would refer to those types of forces which cause the molecules to stick together as London dispersion forces. So London dispersion forces are not very strong. We can abbreviate that as LDFs, and every single molecule does at some point exhibit London dispersion forces. Now, if we're going to be taking a look at those, we could rank them according to their different strengths, and we'll take a look at that in the next slide. A second type would be the dipole-dipole. Okay, this is for polar molecules like the example of water. And so those are going to be a little bit stronger because they are permanently going to be polar here. And then lastly is going to be a very special type called hydrogen bonds. Obviously, it's going to be involving hydrogen with certain other elements out there. And so this is going to be my weakest. The London dispersion forces are going to be the weakest. The dipole-dipole is going to be second in the rank. And then lastly is that special case of hydrogen bonds, which are indeed very strong. Okay, so we're going to be just taking a look at those in turn and investigating those just a little bit more as we go. So the London dispersion forces, okay, I did describe for you, they are temporarily going to be stacked up. The electrons are going to be temporarily just stacked up on one side. Let's take a look at an example of like even helium. Okay, helium itself has 2 electrons, okay, 2 protons on the inside and 2 electrons on the outside. Even helium, even though it's a noble gas, it doesn't really tend to bond with anything. We will find times where these 2 electrons might be stacked down here, making it a temporarily positive side over here. If there's another helium in the vicinity that's doing the exact same thing, those electrons would actually stick here in London dispersion forces. Now that's going to be a very weak bond that's easy because those electrons continue to move. It will just temporarily stick, and so it would have a very easy time to separate off again. If I was going to take a look at this in terms of just temperature taking it apart, helium would boil at negative 268 degrees Celsius. Okay, that's all it would take to get this to boil, and that would excite those electrons. Okay, they're very easy to separate. But if I looked at something a little bit larger, something like argon. Now, argon has 18 protons, so that means that it has 18 electrons out there, and so there's a lot more electrons to play with out here, and they're more likely to get stuck on one side. And so the boiling point of this would be a negative 186 degrees Celsius. If I take a look at an even more complex molecule like methane, we'd have CH4. So there are going to be, even though it's non-polar, we would see that I've got these electrons that are sharing back and forth, and indeed there are times it gets stacked up a little bit more, and so its boiling point is a negative 161 degrees Celsius. If I look at something even more complex, if we had like C8H18, I would have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and all these are going to be hydrogens. Well, look at all the different opportunities there are for electrons to get stacked up. And so the more complex we get with this, notice with this one, there's way more electrons, and so its boiling point is going to be 125 degrees Celsius, positive 125. And so the concept is, as the molecule becomes larger, okay, the attractive force becomes harder to pull apart. So the strength of those, the larger the atom, or the larger the molecule, the larger the LDF force. Okay, so that's the concept behind it. Okay, and so again, that's just the concept behind my LDFs. Now let's take a look at my dipole-dipole. Okay, this is the time when we get unequal sharing of electrons. The example being water. And so it is permanently in this state. And yes, there's going to be London dispersion forces that are applying here. They happen with every single molecule and atom. But we also see, if I put another oxygen here and my hydrogen here, notice that this is a partially positive side that would stick to the partial negative side. And so those forces are going to be attracting to one another, and water becomes almost sticky, if I was going to describe it that way. It's permanently electron heavy on one side, so it's going to have a much higher boiling point than the London dispersion forces. Now, we have one last example here, and that would be in the case of the hydrogen bonding. Now, these are very special dipole-dipole forces. Very high incidence of this, and that's because we have hydrogen bonding in a very special way with three different elements out there. And we always think of the hydrogen bonds with my phones, my fluorine, my oxygen, and my nitrogen. These are very high energy attractive forces. You see all the electrons around here and none around here. They're just sharing back and forth. So we see that's one case. My water would be a case also of a hydrogen bond. Okay, there's my oxygen. And so if I take a look at one more with the case of ammonia, that's hydrogen that's going to be bonding with nitrogen 3 times. Nitrogen, it is going to be a polar molecule, so yes, it's going to be exhibiting dipole-dipole forces, but this hydrogen bond here is an extremely strong one as well. Okay, that involves the hydrogen bonding. Okay, so that's the concept within those 3 types of forces that we find of intermolecular forces. All right. Now, I want to see how we're doing with this. And in class, we're going to be taking a look at these scenarios. These are very common questions that we would be finding on an AP exam. So let's take a look at the forces that would be present in these different cases. All right, we're going to rank them in order from lowest to highest boiling point. Now remember, when we're doing that, we're saying the weakest bonds to the highest bonds. The key to all of this, guys, is to draw it out. Always, when I see CH3OH, we're going to be drawing it like this. Okay, with a hydrogen here, I see we have an oxygen, and we have my hydrogen. And then I'd have to get those dots in there as well. All right, so this means that I'm going to have a negative side, I'm going to have a positive side. So let's take a look at what we find. We're always going to find LDFs. Okay, that's a given at any given point. Is this thing polar? Yes, it's polar right here, and so we would find the dipole-dipole forces being present. Do we have an example of hydrogen bonding to my phones? Yes, I've got an example of hydrogen bonding to oxygen, and so we'd also find hydrogen bonding here. This is a very strong bond, so I would definitely be saying if I was going to be ranking them from lowest to highest, that's going to be a big player. Now, I take a look at argon. Okay, argon is atomic number 18, and argon is a noble gas. Okay, does it have London dispersion forces? Of course it does. They always do. We're going to find times when they're stacking up on one side. Is this thing polar? No. It's just a simple atom that's not bonding to anything, and it's not involving hydrogen, so I would see that we'd only be finding LDFs. Okay, that's going to be a very weak force. Now let's compare that to something like neon. Neon as well is a noble gas. Okay, so the question is, it is going to have the LDFs, okay, but this is atomic number 10, where argon is going to be atomic number 18. So we have fewer electrons, and so that's going to be the weakest of all of them because there aren't any there are fewer electrons to play with at this point. Now let's take a look at one more example with my CH3OCH3. If I was going to draw this out, I'd have my carbons and my hydrogens, and I would see the oxygen here. And this is now bonding to a carbon, which is bonding to hydrogens. So you see the difference between these molecules is my hydrogens are bonding to carbons. Over here, my hydrogen was bonding to oxygen. This is not an example of hydrogen bonding, though, is it? Because hydrogens are not bonding to my phones. So be watching out. Always look for phones, and I don't see any phones here. I see just LDFs, and I see my dipole-dipole. Okay, so now I've got these ranked, and we've got to go from lowest to highest. So my neon is going to be lowest, okay? The next one up is another atom, but it's a little bit more complex atom, and that's going to be my argon. Okay, now those just have London dispersion forces. Now we have a scenario where we have London dispersion and dipole-dipole. So this is my CH3, OCH3, And lastly, we have one that exhibits all three types of bonds. And so that's going to be my CH3OH. You wouldn't know the difference just by looking at the chemical formulas. Draw it out. Got to do it. All right, so there's how we take a look at figuring out and ranking those. Let's take a look at a couple of other examples to see how we're doing. Okay, what determines the strength of those forces? What's going on here? Well, what's happening with dipole-dipole forces is this is going to be the unequal sharing of electrons. Okay, they get electron heavy. Okay, that's going to be there. So what's going to be determining the strength? We're going to be taking a look at valence electrons and seeing that differential between those. Okay, the strength of the bonding, it's really literally going to be with those three atoms. So the strength of the bond comes from hydrogen bonding with those three. And then with the London dispersion forces, well, we've got a couple different things going on. Remember, it's just accidentally getting into the electrons on one side. So if we're looking at an element, okay, we got to go and refer to our periodicity. Periodic trends are very important. Okay, as we go further over, there's going to be more electrons in there. As we go further down, we're going to be adding shells on there, and so that makes it more complex. If we take a look at diatomics, if I was going to take a look at diatomic atoms, well, here we're going to be referring to my Coulomb's law, and certainly Coulomb's law applies to the element as well. But in terms of Coulomb's law here, we would see some examples of how many electrons are going to be shared and what's that differential. Again, it gets into the shells. And then if I look at my molecules, then we would refer to the size. Okay, the size of the molecule, the larger it is, the more force it takes to pull apart. Okay, so that's an example, or how we would sort through the different strengths of the forces between those intermolecular forces. Okay, now another thing that you're going to be doing on an AP exam is maybe having to draw a picture to delineate what's going on with an ion-induced dipole. Okay, so let's take a look at an example of what we might mean by that. Let's look at, say we've got salt again. We've got some kind of ionic compound in here. Okay, and I'll just draw a couple of these out here. So there's my crystal of ions, okay? And we're going to be taking a look at how an ionic-induced dipole is going to be working with that. So we've got my salt here, and it's sitting in with water, okay? This is a dipole, and notice that my negative side here is not going to be attracted to that piece, is it? But if I have another water molecule like this, I know I'm putting it out of the container, but you bear with me here. This is a partial positive side, and so this thing is going to form an ion-induced dipole, and so this hydrogen will pull off this negatively charged chloride. That would then open up this negative side to the positive side here, and that would form a bond. So we could actually get those things. It's not a strong bond, but it is an example of an ion-induced dipole for an intermolecular forces. Okay, so that would be what's going on in that type of an example. How about a dipole-induced dipole? Okay, a dipole-induced dipole would be that an example of the water that I showed you before. Okay, so let's take a look now at some intermolecular forces that we'd be finding here. Now remember, you're going to be going and drawing everything. Okay, I see it's just an element, neon. Once again, I know we did this one already, but it's a noble gas, and so this is just going to be LDFs. That's it. When I see I have my nitrogen with my hydrogens, okay, first of all, we're always going to be finding on every single one of these LDFs. LDF for everything. London dispersion forces are present in everything, holding them together temporarily based off of the just chance that electrons are going to be stacked on one side. This is also polar though, isn't it? And so we're going to be finding, in this case, it's going to be dipole-dipole. Now remember, this is one of my phones, and so this has hydrogen bonding. Now let's take a look at my potassium chloride. If I was going to draw this one out, here's my potassium and here's my chlorine. Okay, we've got my LDF in there. Is this thing polar? Yes. And so this is going to be a dipole-dipole. Does this involve hydrogen? No. Now we have also my phosphorus, or sorry, yeah, my phosphorus with my hydrogen. And be careful, I know I keep on saying phone, and we don't spell phone with a P in this case. Remember, we're only looking for fluorine, oxygen, and nitrogen. So I would have definitely polar. This is going to be dipole-dipole, but it is not hydrogen bonding. Okay, we take a look now at boron dichloride. Boron dichloride is kind of a weird one, but when I draw it out, it looks like this. Boron is only one that has 3 valence electrons to play with, so that's why it looks the way it does. And yes, it is going to be a polar, so that's going to be dipole-dipole. Sodium chloride in water. Now, be careful because sodium chloride in water is just looking like this. Okay, it dissociates, and so it acts independently on there, and so it is not going to be polar because it will dissociate into the ions. It is ionic in nature, and so we don't apply dipole-dipole. That's going to be if it's only molecular. So that's why it's only going to be LDFs on this one. And I guess we should say you can think of this as a dipole-dipole if it's in an ion-induced dipole rather than the molecular type of dipole. Okay, so I would take dipole-dipole on this one. Now, we take a look at one last one here, C2H6, and so that's going to be 2 carbons together, and here are going to be all of my hydrogens surrounding it. It's non-polar, so it's not a dipole-dipole, but I do see carbons, and I see these are all hydrogens, but it's not one of the phones. So this is going to be LDF only, okay? So let's take a look at another question that you guys are going to be answering. Okay, there we go. Which of the following molecule pairs is not involved in hydrogen bonding? Now I see hydrogens in everything, so we can't really answer that question too readily without drawing it out. Have I said that before? I think I have. If I'm going to be drawing out this particular molecule, I'm going to be seeing that my hydrogen is here, my carbon is going to be there, and I've got my oxygen here and my hydrogen here. Do I have a case of and then my water, we've drawn that out enough times. Do we have a case of hydrogen bonding? Yes, we do. We have my phones in this case. So I see this one, and remember the question is asking which does not, so we know that this has hydrogen bonding. I know this is hydrogen bonding, and we just did the nitrogen with my hydrogens. This is ammonia. And this has hydrogen bonding because this is one of the phones. Now, the question is this hydrogen sticking to the oxygen? Is this hydrogen sticking to the oxygen? The only way to know is to draw it out. And so we see that we've got, on the first case, and where does that hydrogen go? That hydrogen is attached to an oxygen. How about the case of my acetic acid? We see that I have my hydrogen. Here's my carbon. And this is another carbon that's sticking. And let's see, I've got an oxygen here. And yep, it is in fact attached to a hydrogen. Now, the last one, we see that we've got hydrogen bonding to hydrogen, and we have iodine bonding to iodine. Okay, hydrogen bonding to hydrogen. Hydrogen has to be attached to my phones. Okay, so it is not going to be, this is the example where hydrogen is not, hydrogen bonding is not found. Okay, so that's how we approach those types of questions. You got to draw it out first. All right, let's take a look at which ones then are going to be London dispersion forces. All right, so draw it out. Let's see. To find my sulfur dioxide, the question here, guys, is if we're going to be finding if it is polar. Okay, that's how we know. And if I find sulfur dioxide, it's going to look like this. Oh, this is polar. Okay, that's got my London dispersion. They all have it, but it is also polar. Now, carbon tetrachloride looks like this. Is this thing polar? No, it's not polar. So this one is going to be LDFs only. Let's take a look now at my CH2Cl2. Okay, if I have 2 hydrogens, they go like this, and they can be on either side, doesn't matter. Oh, but my chlorines, they have those extra electrons around there. That makes this extremely polar. So this is a dipole-dipole. Okay, that doesn't count. Last one we're going to be taking a look at is H2S. And so This looks like a water molecule with sulfur instead of oxygen, and so this is polar. And you might also ask, is this going to be a hydrogen bond? No, it's not one of the phones. But the question is only asking about London dispersion. Since it's polar, that doesn't work either. All right. Now, moving into the last one, we've just got some drawings to do because, again, the AP board wants to see, can you actually demonstrate your understanding of these different forces? Okay, so we have three molecules of carbon dioxide in a state of matter according to what's below the box. And here's my liquid, here's my gas. Okay, what does carbon dioxide look like? Okay, if it's in a liquid form, those molecules are going to be closer together. And so there's my carbon, and here's two oxygens in there. So what's going to happen is those molecules are going to be closer to one another, and so there's going to be more force that's going to be interacting with each other. And so this is where my intermolecular forces are going to be affecting one another. The intermolecular is going to be in here. If I was looking at the bond between my carbons and my oxygens, this would be my intramolecular forces, okay? Because it's going to be found inside. Now, if it's in a gas form, again, we've got the intramolecular force, but in a gas form, they're a lot further apart. Okay, so we wouldn't find much of a force in here. Here's where my intermolecular forces would come into play. Between the two molecules, much more space in between, so much weaker force. Okay, and so that's how we approach those types of questions when you have to draw it out. Definitely exaggerate the different states of matter. Notice that I did do a little bit of space in between on my liquids in there, so just kind of be careful for that. Which of the following drawings best represents a hydrogen bonding in this molecule? So this is a pretty easy thing to take a look. I see that I've got hydrogen bonded to oxygen. I see I've got hydrogen bonded to oxygen. I see I've got hydrogen bonded to oxygen. And I see I've got hydrogen bonded to oxygen. So the question is, which one has the best representation of hydrogen bonding? Okay, is what they're getting at is, here's one molecule here, here's one molecule here, holding to one another. I wouldn't say that's hydrogen bonding there. We see that the hydrogen to hydrogen, but here I see this hydrogen is bonded to that oxygen. Okay, here's one molecule, here's another molecule, here's where they're interacting, and you'll notice on this one it's hydrogen to hydrogen again. So we pick those apart in there, and I would definitely say picture 2 is the best example of hydrogen bonding because it's the hydrogen going to a different molecule. Okay, the complete drawing of your methanol is shown in the box below. Molecules of methanol can form hydrogen bonds with water. Okay, in the box below, draw a water molecule in the correct orientation, okay, with the molecule of methanol. So used a dashed line to represent that hydrogen bond. Now, here's the key. Here's an oxygen. Who does he have to bond with? I'm going to put my hydrogen real close to that. Okay, here's my water molecule. Let's get my dots in there. And they say to use a dashed line to represent that bond. If I look on this side, this hydrogen will be also have the opportunity to bond. Sorry about that. And use that dash line and definitely represent it that way. Okay, that's the hydrogen bond. I would definitely draw it on the hydrogen as well as the oxygen side to demonstrate that methanol will in fact have those forces on either side. Okay, so watch out for those. Those are some of the skills. Okay, from here, we've got some other types of examples with that, but that sums up all the different forces for intra and intermolecular forces. We did find quite a few of those types of questions on last year's AP exam. So good luck to you guys. I think you're going to find this comes together pretty easily.